Okay, so in the last class we started with the band theory of metals, right? And what we saw first, we actually discussed a little bit of that background, like how the molecular orbital theory works. When two atomic orbitals they come together, they form two molecular orbitals, and electrons are occupied from the lowest energy level to the highest energy level, right? For example, in hydrogen's case, we saw that there are two atomic orbitals which are coming together, 1s orbitals, and then two molecular orbitals with different energies, and both the electrons are occupied in the lowest energy state. And so basically this is also, we can say that this is actually splitting of energy band, because 1s energy band or energy level is getting splitted into two different energy levels. So this is called splitting of energy bands. And then this concept, when we apply this concept on a solid, where actually number of atoms are in the order of Avogadro's number, 10 to the power 23. So that means when 10 to the power 23 of that order atoms are coming together, they will form as many number of energy levels, right? And again basically energy splitting will happen, but in case of solids, this, because this energy range is very small, for all practical purposes actually it is a continuous band. Within a energy, within a band, the energy levels are basically continuous, right? That's what we said. In case of solids, because the energy range in which the energy is getting splitted, that is very small in comparison to the number of energy levels, for all practical purposes actually they form a continuous band. And additionally, in case of metals, what happens is that different bands also overlap with each other. For example, in this case, in case of lithium, 2p band is the bottom of 2p band. It is some part of it basically is overlapping with 2s band. So that is why from the lowest energy level up to the vacuum level, after which the electron becomes free, right? So basically, till that level, we have a continuous band of energies. There is no energy gap as such. So that is why we represent the band formation or the band diagram of metals in this way also. Like there is a 2s band, and some part of it is getting overlapped by 2p band. Similarly, to some part of 2p band is also getting overlapped by the bottom of 3s band. And the electrons are occupied in, on, they are filling up only half of the energy states in 2s band, because actually there are n number of atoms. When they overlap, they form n different levels, and only half of them will be occupied, because one energy level will contain two electrons of opposite spins. This is all what we discussed. Then these were some simple definitions, like how we define Fermi energy is. Fermi energy is actually the energy level up to which all the energy levels are occupied. Basically, the energy up to which all the energy levels are occupied. And usually we measure the Fermi energy from the bottom of the band. So this is the Fermi energy, and the energy which is required to free an electron into vacuum from Fermi energy level, that is known as work function of a metal, right? So if we basically add work function and Fermi energy, that will give us the highest amount of energy which will be required, because see, the lowest energy electrons are here, right? So if we want to move them into vacuum, or we can basically we want to say that we want to make them free, the energy which will be required, that will be Fermi energy plus work function. Then these are some, very basic examples of, in metals we can have different Fermi energies and work function. If there are any questions, I just had a very quick recap. If there are any questions, we can take them up now from the previous class. Otherwise, we will start with this new topic. Are there any questions? Okay, if there are no questions, let us start with today's class. So what we have seen so far, energy splitting, then continuous band of energy is getting formed, and band overlap in case of metals. With that context, Let us try to understand how electrons will behave in this new picture of material, right? Whatever we have seen so far, that was actually classical. There is a question. Let me have a look at that. Why is the surface potential energy considered to be zero? It is not surface potential energy. See, actually you can take, that is why I defined this very clearly. You can take either zero here, like basically we are saying is, what we are saying is, when the electron is moved into vacuum, the electron is free, so that's why its energy is zero. So we can take either Fermi energy from here, like we can also measure this difference, and we can define the Fermi energy in this way. But conventionally, what is followed is, we measure the Fermi energy from the bottom of the band, and then this difference we call as work function. So this is actually because potential energy, you must be knowing, potential energy is a relative term. So we can define our zero here. Accordingly, all the other energies will be negative afterwards. If we define our zero at the bottom of the band, all these energies will become positive, of course, right? So potential, because potential energy is something relative, we can define our reference level wherever we want. Usually we try to follow the conventions, and in this case convention is, we define the zero at the vacuum level. All the energies are basically negative. Is that clear? Actually, that is what is shown in this picture also. If we define zero here, then this will be 4.7 electron, the Fermi energy will be 4.7 electron, and work function will be 7.2 minus 4.7. If we define our zero here, then this will be minus 2.5, and this energy level will be minus 7.2, right? Okay. So let us try to understand the behavior of electron now, right? So what we have seen so far is that only half of the energy levels are full, so all the electrons are occupied in half of the energy levels, and this energy is defined as EF0, because we are defining Fermi energy at zero temperature. All the energy levels which are occupied at zero Kelvin temperature, and that energy level is known as Fermi energy. And then let me get my laser pointer here. So all the energy levels which are above the Fermi energy, they are free, right? They are basically not occupied, they are unoccupied. Now if we try to see how the electrons, if we try to form the how the energy and momentum of an electron is related, that is related by this relationship which we have already seen, p square by 2m, that should be equal to energy, right? That is the kinetic energy of an electron. And because in metals electrons are free to move around in the crystal, we assume that their potential energy is practically zero. So all the energy is contained only in kinetic energy. So their energy is, in this case we can define the relationship between energy and momentum, that will be is equal to p square by 2m. And that is what we have plotted here also, right? Now when we apply when there is no electric field, what will happen is that there will be some electrons which will be moving in the plus x direction, so basically their momentum will be positive, and there will be some electrons which will be moving in the minus x direction, so that their momentum is actually negative. So for every positively moving electron, there is a there is an electron which is moving in the negative direction also. So basically their their momentums are getting cancelled, right? So that is why average momentum of the whole crystal will be is equal to zero in this case, when there is no electric field. That is actually what we have seen in classical picture also, that when there is no electric field, the average momentum or average drift velocity is zero. So that is what we are seeing here also by plotting this energy versus momentum curve. Now what happens when we apply this electric field? Let us say we are applying the electric field in minus x direction. If we apply minus x direction, that means there will be a force on electron in the plus x direction, right? So what will happen is, the electron which was here, this electron which was here, it will gain some moment, gain some acceleration, right? Because electric field there will be a electrostatic force which will be applied on this electron, which is moving already in the positive x direction. So that means its momentum will increase. It will go from, let me just, let me delete this actually. This, yes. So what will happen is this electron which was moving in the positive x direction, it will gain some acceleration, and because of that its average velocity will also slightly increase. So that's why it will move from point A to actually A prime, right? Similarly, what will happen, the electron which was at position B, it was already moving in the minus x direction. So that means there will be a deceleration which will work on this electron, and because of that its velocity in minus x direction, that will decrease. That means its momentum will actually go down. So it will move, the electron which was here, it will move from this position to actually from B to B prime, and from A the electron has gone to A prime, right? And why this can happen is, why this electron from A can go to A prime, because actually all these states are unoccupied. If these states are not unoccupied, means which means they are full, or they already have electrons, then this movement is not possible, because there has to be an empty energy state, then only electron can go to that energy state. If the energy state is already occupied by the electrons, it cannot go from A to A prime. But we know that at 0 Kelvin temperature, above Fermi energy, all the states are unoccupied. So that's why this electron from A, it can go easily to, it can gain the momentum and go easily to a position which is represented here by A prime, right? So now what has happened actually? Our curve has slightly bent here, right? Previously it was centered at 0, which means the average momentum of the whole system, of the average momentum of all the electrons was 0. Now it has slightly shifted toward the positive x direction here, right? So that is why average momentum of all the electrons will be greater than 0, which means there will be a effective movement of electrons in the positive x direction in the presence of electric field, and that is what is expected also. But this is what actually happening at the quantum level. We are trying to look at the quantum picture, how this actually happens, right? And I will actually point out what a major difference, although the outcome is same, that the electrons are getting shifted toward, now they are effectively moving towards positive x direction, but there is a big difference how that is happening. I will point that out in the course of our discussion. All right, so now this curve has slightly moved in the positive x direction, and there is a effective positive momentum, average positive momentum. Now if you look at the electrons which are below this level, all the electrons, basically for every positive electron, I mean, please try to understand, positive, by positive electron I mean that the electrons which are moving in the positive x direction. So for each positive electron there is a negative electron also. So all the momentums below this level, they are all getting cancelled with each other. Only electrons actually which will participate in the conduction, or basically which will give the average momentum in positive x direction, are only these electrons, right? The electrons which are in this range. What this means, effectively it means is that all the electrons are not participating in the conduction process. There are only very few electrons which participate in the conduction process, and those are the electrons which have energy very close to Fermi energy. Although we have actually exaggerated this range here, but actual in reality this range is very very small. Like this delta E which you are seeing here, delta E is actually much less than EF. So this range is very very small. So what we can effectively say is, the electrons which are at the Fermi energy level, only those electrons are participating in the electrical conduction of a metal, right? And what happens is that when so these electrons are moving in the positive x direction, right? So what happens is that this electron will again go through some scattering process, right? There will be some scattering source, it will collide with that scattering source, and then it has to change its energy as well as momentum, right? So basically it will move, it will go and come back. Basically it will get scattered, means before scattering it was moving in the positive x direction. After scattering it will move, because it has to change its momentum also, right? So it will start moving in the negative x direction. So basically this electron will move from this position to this position, and the 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 position at a prime, that will be taken by the next electron which is there in the line, right? So that is how this process is going on continuously in a steady state. That is what is happening continuously. The electron at a prime, that is getting scattered, and it is, after scattering it is going to b prime position, and the position with the electron which is just below a prime, that will move to the a prime position. So in a steady state this continuous movement is actually going on. But in this whole process, the electrons which are participating in conduction, those are only the electrons which are at the Fermi energy level, right? So this point is very very important here, which is very different from the classical picture. In classical theory, we assume that all the electrons are participating in the conduction process, which is actually not true. There are very few electrons which are at the energy level, only they are participating in the conduction process. And then conduction occurs by the drift of electrons only in the energy levels between b prime to a prime, right? From b prime to a prime, and this energy range is very very small, very close to the Fermi energy. There is a question: how the electron at a prime is scattered? There were no electron nor impurity was present there. Let us assume that there are no impurities. Even after that, atomic vibrations are happening, right? So there is one scattering event which is also because of the atomic vibrations. Atoms are vibrating along around their equilibrium positions. So electrons can get scattered by the atomic vibrations also. And in any material, actually no material is ever perfect. In any material, you will always have some concentration of impurities. Oh, at 0 Kelvin are there vibrations? No. So that is actually a very good point. Somebody just wrote that at 0 Kelvin are there vibrations? No, there are no vibrations at 0 Kelvin. So these scattering events have to be actually different type of scattering, like impurity scattering, or some other type of scattering. That's a very good point. Thank you for pointing out. But there will always be some scattering sources, and if there is no scattering, we know that actually resistivity will be infinite. But that can never happen practically. That is never achievable. There will always be some defects or impurities, or some sort of scattering events will always be happening. Okay. Any other question? Okay. So from this slide, actually, the message which you should take with you is electrons only at the Fermi energy level, they are participating in the conduction process. Everything else is basically for you to understand why we are saying that, but that is the main takeaway message from this slide. All right. So let us move. Now, actually, we can use this theory for explaining conduction in a different way also. Like, we have already seen, that we can represent the band diagram in metals in this way, right? So, through that diagram also, we can explain the conduction here. So, what you are looking at in this picture is we have our material here, and then we are applying a voltage. Applying voltage is equivalent to basically applying an electric field, right? So we are applying an electric field on this material in the minus x direction. What will happen? So now the potential energy, because of the application of this electric field or the voltage, the potential energy of electrons will be minus E times Vx, right? That will be the potential energy. If we are applying a potential of V, the potential energy of electron, that will be E times minus E times Vx. And this voltage in the material will be changing by dV by dx is equal to minus Ex. Ex here, actually this Ex is electric field, and yeah, so basically V will be a function of x, isn't it? V is equal to minus E times x. So because of that, electrons gain electrostatic energy as it moves in the positive x direction. If an electron is moving in the positive x direction, electrons which are at the Fermi energy level, they will be moving in the positive x direction, right? And when they are moving in the positive x direction, there will be a gain in their electrostatic energy. Now, actually, to take into account this gain in the energy, gain in the energy of electron, this Fermi energy level will be actually tilted because electrons, the the energy of electron at zero will be EF zero or Fermi energy, and then when it reaches at the other end, the energy of the electron should be EF zero minus times EV. So that is effectively the tilting of band diagram or tilting of Fermi energy level. And now you can visualize, conduction, basically conduction as drift of electrons drifting down, or drift of electrons, down the potential hill which is getting formed here because of this application of this voltage, right? So there is a potential hill through which electrons are basically drifting down, right? This bending of energy band should be understandable, right? Because the energy of electron will be EF0 here, and when it reaches the other end, because it has gained certain electrostatic energy, it should be EF0 minus E times B, right? So that is why this bending of this energy band happens because of the application of this potential or the voltage. And then actually this is for the visualization sake, actually this is kind of a potential hill, so electrons are drifting down this potential hill, and that results into the electrical conduction. One thing you should remember is that although the average speed of electrons is 10 to the power 6 meter per second, the drift velocity, which actually is a measure of how fast is electrical conduction, that is only in the range of 10 to the power minus 2 to the 10 to the power minus 1. Why? Because actually electrons are going through various scattering events, so that's why their drift velocity is much lower than their average speed, right? So that is how we can visualize conduction in these, in terms of band diagram. Any questions so far? I have actually explained the conduction qualitatively now. Now we will look at the quantitative picture of this conduction also in a couple of slides, in a few slides, maybe in this lecture or maybe in the next lecture. But this is the qualitative picture how this happens. Basically, the electrons which are at the Fermi energy level, they are only those are the electrons which participate in the conduction, and then because of this gain in the electrostatic energy of electrons, there is bending of the band diagram, and electrons simply drift down this potential hill, and that results into conduction. Any questions on this? You can take a minute or two to think about whatever we have discussed, and if you have any questions, you can just unmute yourself and ask if there are any doubts. All right. If there are no doubts, there is a question. After A prime position, electron has to revert back to position B prime. Yes, actually, why is that happening is because of the scattering. Once it has reached A prime position, the electron which was initially at A position, once it has reached to A prime, which means basically by gaining the momentum, it has reached to A prime. It will go through some scattering process, and because of that scattering, the momentum of the electron that has to change significantly, right? So basically electron has to start moving in the negative direction. Only the energy states which are available in the negative directions are actually states above B prime level. So naturally it will try to go to the lowest possible position, right? So that's why it will move to this position B prime. Sir, is there any significance of potential hill in conduction? Because ultimately conduction will be as mentioned in slide 13. See, significance means, this is like, if you look, this is the mechanism of conduction. What we are discussing in slide 13, That is the mechanism of conduction. But later on, when we have to define quantitatively how fast the conduction is happening, then these will be important, right? That how much energy is gained by the electron, what is the Fermi energy. All these things will start coming into picture when we start discussing the quantitative picture of conduction. But mechanism wise, this is what is happening at the electronic level, right? So that is why this bending of band diagram is important. And actually, I mean, bending of the band diagram is also to visualize, like, you can simply see that there is a potential hill which is getting formed, and then it is the electrons are just sliding down this potential hill. So yeah, I mean, in a way you are right that the real picture is this one. And for sake of, ease of visualization, we are trying to make this picture of bending of band diagram also, right? Okay, so then let us try to move. So these actually, I will introduce couple of concepts of, one is effective mass, and then next is density of states. These are actually built up to the quantum theory of metals, which we are going to, talk about after introducing these two concepts. So because, you might be wondering why suddenly we came to this effective mass of electron. So these two concepts of effective mass and density of states, they are the building blocks of quantum theory of metals. So that's why we are discussing them here. Okay, so what happens, like, how do we define, like Newton's law of motion is acceleration should be is equal to external force divided by the mass of that body, isn't it? We have seen this Newton's law of motion, that acceleration is defined by this actually, that it should be is equal to external force. This keyword external is very important here. The force which we are talking is external force divided by the mass of that particular body is the acceleration. So if we want to apply this to electrons also, let us say if an electron is in vacuum, electron is in vacuum means it is not in, I mean, there is no other interaction. Like electron does not have any other interaction with other electrons or protons or any other thing. So that means if we are applying, if in that case, if we apply an external force, we can say that the acceleration of electron will be F external divided by ME, right? Because there is no other force, there is only external force and no other interactions. So that's why the acceleration of electron will be F external divided by mass of the electron. Now let us try to see what will happen when the electron is actually in a crystal, because electrons are very rarely in vacuum. I mean, other than except very few specific applications, electrons are always in crystals basically. So the acceleration of electron in a crystal, we want to apply this definition actually, that it should be, the acceleration should be is equal to F crystal, which means the F external which we are applying, sorry, sorry, I'm very sorry actually for this confusion. So actually, if we want to define the acceleration of an electron in a crystal, that will be is equal to the electron, the force which is experienced by electron in the crystal divided by mass of the electron, right? And if we are applying an external force when the electron is in crystal, we are still applying an external force, but in addition to external force, there will be some internal forces also because of interaction of electrons with the atoms as well as other electrons, right? There are a lot of electrons in the crystal as well as there are a lot of atoms. All of them will be applying some force on this electron. So in addition to this external force, there will also be a internal force, right? So if we want to see what will be the acceleration of an electron, that will be F external, which we are applying from outside. Sorry, there is a typo here. And there will be F internal. This will be the resulting force or the net force on the electron, and that will be divided by the mass of the electron, right? What we want to do actually is we want to write this thing, this whole expression as F external divided by ME, some sort of mass of electron. So ultimately, what we want to do is we want to take into account the effect of F internal and incorporate that into mass of the electron, so that every time we don't need to worry about what are the internal forces acting on the electrons. Okay, so what we want to do is we want to equate these two equations. So for that, what we need to do is we need to take the effect of internal forces on electron and accommodate those or incorporate those effects into the mass of electron. Okay, and that is why this concept of effective mass comes into the picture. We don't take the rest mass of the electron or the mass of the electron which will be in the vacuum, but an effective mass, so that we can write this simplified equation simply that a crystal should be is equal to F external divided by the effective mass of the electron. Okay, so electron will appear to be exhibiting a different inertial mass, right, because of the effect of F internal, and this effective mass is, it takes into account the effect of internal forces. Okay, concept of experimentally it has been found that concept of effective mass is found valid for the electrons in partially filled bonds, only in the partially filled bond, because when the bands are sorry bands when the bands are fully occupied, then the movement of electrons is very difficult, right, because all the energy states are occupied. So only when this concept of effective mass of electron is usually applied only in the partially filled bonds, partially filled bands, when there are some energy levels occupied and there are also some energy levels which are unoccupied, which are available for occupation. Okay, I hope, I mean, actually, the concept is very simple. We want to take into account the effect of internal forces on electron and put that into the mass of electron, and that's how we define effective mass of electron. Any questions on this? I confused a little bit in the beginning, but I hope it is clear now. Any questions in this? So naturally, this effective mass will depend how strong are the internal interactions, right? How strong are the interactions of electrons within the system. You can see that for some of the metals, for example, silver, this is very, like, the effective mass is equal to the rest mass of the electron. But some of the metals like gold, it is 1.1, and for bismuth it is very very small. Small effective mass will mean that the internal interactions are very very strong, isn't it? So that is why there is a we get such a low effective mass of electron in bismuth. For copper, again, it is very close to the rest mass of the electron. For potassium, it is slightly higher. For lithium also again. So basically, for different metals, it is actually a intrinsic property of a material. The effective mass of electron, it is an intrinsic property of material. And you should also remember that effective mass of electron is a quantum concept. In classical concepts, in classical picture, you do not. I mean, we don't talk about the effective mass of the electron. Okay, and this actually it is not very difficult to find, although the simulations or the calculations are a little bit involved. But because solids which we are discussing, they have periodic boundary, like they have a periodic structure which can be repeated infinite times, right? So because of this periodicity, we can calculate the forces or the potentials which are working on an electron, and then we can incorporate those into mass of the electron to calculate the effective mass of electron. This is actually very what do you say, standard calculation in quantum mechanics. You can calculate the effective mass of electrons. Uh, can you explain the reason behind very high effective mass in nickel and platinum? Let me see. I haven't thought about it. But let me see. So in nickel and platinum, we have very high effective mass. Let us go back to the previous slide and see what happens actually. What does that mean? So if you have very high effective mass, that means a crystal will be much lower. Like if there was only, if there, like, if the electron was in vacuum, the acceleration will be much higher in comparison to when the electron is in crystal, if the effective mass is very high, right? That means the forces which are there, the forces which are there, they are sort of slowing down the electron. They are binding the electron to the to their atoms, or basically to their parent atoms, right? I mean, higher effective mass will ultimately mean that the the effective the effective acceleration which we will get, that will be much smaller in comparison to what we will get in the vacuum. That means the the binding or the affinity of electrons with the crystal structure is very very strong. So I mean, right now I can just explain this much, but I cannot tell further reason why that happens only in nickel and platinum. For that, actually, we will need to see what is the atomic structure of nickel and platinum, and what kind of bonding happens in nickel and platinum. But you should be able to see that if the effective mass is higher than the rest mass of electron, that means the electron is more bound into the crystal. It is more difficult for the electrons to gain acceleration. If the effective mass is smaller, that means electron is more free to move in the crystal. It can gain the acceleration much more easily in comparison to vacuum. All right, let me see. There are some other questions also. Hmm, I hope that satisfies your question. Next question is fully filled. That's why. Okay, somebody has tried to answer why it happens in nickel and platinum. Somebody said it might be fully filled. That's why. I'm not sure. I mean, I don't think uh, that the bands are fully filled in nickel and platinum, because they are also metals. And if it is fully filled, then it will be an insulator. I'm not sure. If you want, we can have a discussion on it separately in tutorial or something like that. But right now, I can explain only what will be the effect of lower effective mass and higher effective mass. If effective mass is large, it should mean very weak. It should mean very strong, right? Effective. If the effective mass is larger, that means acceleration will be much lower, right? Acceleration will be much lower in comparison to what it will be in vacuum. So that means it will have very strong internal forces. If the effective mass is lower or small, then it will mean that the 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 interactions are very weak. Internal interactions are weak actually. What about low one as bismuth? How are interactions there? Yes, I just explained that actually. If the effective mass is very low, that means the acceleration gain will be much higher, and that means that the internal interactions are very weak. All right.
Hi, am I audible here?
Yes, Varun, you're audible.
Can I add something here?
Yes, please.
So actually, I think I am not sure if we have already discussed it this way, but can we look it this way that on the top we have numerator and denominator. In that we have F external plus F internal divided by ME, and then we are equating it to F external by ME star. So can we indirectly say that to get rid of F to account for F internal forces is we are expressing ME as ME star. So then we can maybe understand that the ME star might give some idea about how the internal forces are there in crystal.
Yes, Varun, that's what we are discussing.
Okay, okay,
Yes.
thank you.
So here we are considering effective mass by rest mass, and not just effective mass. So higher the ratio, higher the acceleration. Let me just look at this. So if this is higher, that means effective mass will be higher. And if the effective mass is higher, if the effective mass is higher, then a crystal will be lower, right? No, if the higher the ratio, the acceleration will be lower actually, isn't it? Because see, if, let us say if it is 28, that means ME star will be 28 times ME. and if we place that here, that means acceleration will be lower, right? Okay, let me move to the next concept. I mean, if there are still questions, you can type them in the chat box. I think I have answered most of the questions, but I would like to just introduce this concept of density of states also. Okay, in this class itself, because we have very little time left now. So yes, so let us come to the density of states now. Density of states means, before we go there, actually, what will happen? Like, we have already seen that when there are n atoms, forming a solid, there will be interactions of n atomic orbitals, and that will result into n molecular orbitals, and they can interact in different possible ways. The lowest energy one is always in phase interaction, where actually all the wave functions are added together. They are getting added together, right? So this is the lowest energy interaction, because it is the all the wave functions are interacting in phase. The highest energy configuration is this one, where all the wave functions are interacting out of phase. So we have these alternating minus, plus, and minus signs. So this is completely out of phase interaction, right? So, and this gives the lowest energy, this gives the highest energy. But in between these two energy levels, right, in between lowest and highest energy levels, there are many other energy levels, right? Because there are many different combinations of these n atomic orbitals which are possible, right, between these extremes. And experimentally it has been observed that, especially around n by 2, there are usually the density of states is much higher. And you can think about it actually in this way, like, if you have uh, let us say if you are flipping.
Professor Abhishek, sorry to interrupt here.
Yes.
Hello.
Yes, sir.
Actually, I think some student is facing the voice issue. He has written, your voice has become low.
Anyone else facing the issue, or it's no, right? Others are not. I think the voice is fine for most of the people. So maybe you should look at your connection, please. Shivam, please try to look at your network. If others are also facing the same problem, please, you can type in the chat box. Okay, then let me continue. So yeah, what I was saying is that experimentally it is seen that around n by 2, actually, there are the density of states is much higher. The definition of density of states is, basically, you can imagine in a way that it is the concentration of energy states. How many energy states are there between a certain energy range? Density of states is defined such that GEDE is the number of states in the energy interval E to E plus D. Between energy levels E and E plus DE, we have GE times DE energy levels. So actually, in a way, it is the concentration of energy states in a particular energy range, right? So that is how we define the density of states. To understand this point, that why do we have higher density of states at the middle, let us consider that uh, we are flipping the coin, a coin 10 times, right? So number of possible ways that we get 10 times heads, that will be one. Similarly, number of ways in which we can get 10 times tails, that is also one. But let us say if we want 5 heads and 5 tails, the number of combinations will be much larger, right? So in between, when we are taking, or actually even for other combinations, because here there are the number of possible states itself is one, so that's why it cannot be more than one. But in case when we want 5 heads or 5 tails, or even 6 heads and 6 tails, sorry, 4 tails, the number of combinations will be much larger. So in the central region, we will always have more number of ways, or more density of ways in which we can get those combinations. Similarly, you can, I mean, actually, this is just to, for you to help, intuitively see why is that happening around n by 2, why we are getting higher density of states. So intuitively you can see in this way that number of possible ways at the extreme are always lower in comparison to in the center. So that is why we get this higher density of states. All right. If we understand the definition of density of states, we can write this expression, which is basically number of states per unit volume up to energy E prime. If GE times DE is giving the number of states in the energy interval E to E plus D per unit volume, then if we want to calculate number of states per unit volume up to energy E prime, we have to simply integrate this expression, right? If we integrate this GE times DE, that will give us total number of states per unit volume up to an energy E prime, right? This will be the total number of states per unit volume. This is how we define density of states. Now, if we want to, let us say, derive a expression, let me see how much time we have. Is it okay if we go 5 minutes extra today? Because if I start this, I would like to complete it today itself. Otherwise, there will be break in the continuity. Anyone has any problem if I continue like 2 3 minutes more, like beyond 10? If we go 2 3 minutes, okay. It looks like nobody has any problem. So I'll just try to finish this today itself. So yes, in your earlier classes or discussions, I think you must have seen this expression. If you have not seen, just try to take it on my word that energy of an electron in a 3D potential well is given by h square by 8 mel square n1 square plus n2 square plus n3 square, where actually n1 n2 and n3, they are all integers. This is the energy of an electron in a 3D potential well. Basically, electron is trapped into a 3D potential well. It cannot go out of that potential well. And that is very similar to an electron being in a material also, right? It is very difficult for an electron to escape the material. So it is in a way, it's in a potential well when it is inside a material. So that is why we can approximate the energy of an electron in a material by this expression, which is actually derived for energy of an electron in 3D potential well. Here n1, n2 and n3, they are all integers. This should be actually, E should be in the subscript. I will correct these typos. In the final slides, you will not have this. So this is the mass of the electron, right? Now, if you want to, because what I am trying to do now is actually we are trying to derive the expression from GE, but actually we are going from this side by calculating the number of states which are there below E prime. So we are going from this side. If we can get an expression for, if we can get an expression for SV, we can simply take a derivative of SV and we will get the expression for density of states. So that's what we are trying to calculate here. All right. So if we know this is the energy of an electron and we want to see how many states are there with energy E less than E prime, right? From here we can write that E prime should be is equal to h square by 8 m E n square into n prime square. Now I have written this n prime, but this n prime can be different combinations of n1, n2 and n3, right? This n prime is basically n1 plus n2 n square plus n2 square plus n3 square. This should be is equal to n prime square, right? If this condition is satisfied, then all the energies which with different n1, n2, n3 combinations, they will all be having energy E prime only, right? Now, if we want to find out the states which are having less than, energy less than E prime, this condition, if you are wanting to satisfy this condition, that means n1 square plus n2 square plus n3 square should be less than n prime square, right? For energy to be equal to E prime, it should be equal. And if we want less energy, then that means this should be less than n prime square, right? Now let us look at this picture. What is happening in this case is we are actually rather than discussing directly the three-dimensional case, we are discussing two-dimensional case. So in this case, we are taking only n1 and n2. Okay. So each of these boxes which are plotted here, each of these boxes are representing one energy state, basically one combination of n1 and n2. So for example, this is n1 is equal to 1 and n2 is equal to 3. This one is n1 is equal to 2n, n2 equal to 2. So all these boxes, they are representing one energy state. And if we plot this n1 square plus n2 square is equal to n prime square, we will get this circle, right? This is an equation of a circle. So we will get this circle if we plot this equation. All the energy states which are within this circle, they will satisfy this condition, isn't it? So all the energy states which are within this circular region, they will satisfy this condition. So if we basically calculate the area of this circle, we will get how many energy states are possible, which will have energy less than n prime, right? And that area will be simply 1 by 4 pi n prime square, because n prime will be the radius of this circle, isn't it? Okay, so now let us just extend this to a three-dimensional case. In a three-dimensional case, we will actually get a spherical volume, and it will be 1/8 portion of a spherical sphere actually. So that's why the if we get the volume of this, 1/8 of a sphere, we will actually in that volume this condition will be satisfied, where actually n1 square plus n2 square plus n3 square will be less than n prime square. So this will be the volume in which we will have this condition satisfied in the three-dimensional case. All right. Now, if we want to, if we know this area, which is 1 by 6 pi n prime cube, it is basically, if we calculate this will be 1 by 6 pi n prime cube, right? 1 by 6 pi n prime cube. This volume will be 1 by 6 pi n prime cube, right? So number of this is the number of energy levels. If we want to calculate, let me write this here. Number of states that will be is equal to, because see, these are the energy levels. How many energy levels are there, right? Within which are satisfying this condition. Actually, energy levels which have energy less than E prime, and each energy level can have two electrons. So if we want to calculate total number of states, that will be two times of this volume, right? So that will be 1 by 3 pi n prime cube, isn't it? 1 by 3 pi n prime cube. That will be the number of states which will have energy less than E prime, right? And from this expression, how it is two times. See, because you can, if you can remember from previous lectures, each energy state can have two electrons, isn't it? And state, I actually mentioned this difference earlier also. There is a difference between state and energy states and energy levels, because energy state also has also takes it into account the spin of electron. Like the two electrons which are there in the same energy level, they have two energy states because they have two different spins. All right. So here what we are getting by this volume, that is the number of energy levels, because if you see, this condition will be satisfied if it is less than n prime square, and these are the energy levels, the number of energy levels. If we calculate the number of combinations of n1, n2 and n3 which will satisfy this condition, that those will be the number of energy levels. To get the number of energy states, we have to multiply it by 2. All right. Please again explain why 1 by 3. Yeah, I just explained. We have, if we multiply it by 2, because each energy level can have two electrons, we will have total number of energy states, which is actually 1 by 3 pi n prime cube. After that, the derivation is very simple. We can simply replace, this n prime from here. If we take this equation, n prime will be is equal to actually, sorry, I am not still used to this writing board, so my handwriting is not very clear, but I hope at least it is legible. So it will be, if we replace this n prime, it will be 8 n e l square e prime, 8 n l square e prime divided by h square. This will be, actually this is simply we get from that equation. We will replace this n prime into this equation. That will give us S. Actually, SV was number of states per unit volume, but here we have not taken into account volume yet, so I am representing this by simply S, number of energy states, S. Okay, so if we do all those replacement and calculate this, it will come out to be pi by 3. We have to simply just put this n prime into this equation, and then we will get pi by 3 8 ne e prime divided by h square to the power 3 by 2. Okay, fine. And now, if we want to, sorry, there will be an L cube term also here. There will be L cube because there is L square here. It will be pi L cube by 3h. Yes, yes, that is fine. So this is what we will get. So this is the number of states. We have not taken into account volume yet. If you want to calculate number of energy state per unit volume, we will have to divide it by L cube, right? So this will simply this L cube will disappear. We will get pi by 3, and rest of the expression will remain the same what we have here. And if we want to calculate GE, that will be is equal to DSV by DE. I'm doing very quickly, but if you have any questions, we can discuss them in the next class. So from here, this definition of density of states, we get GE should be equal to derivative of DSV, right? So that's what we have done. GE will be equal to DSV by DE. And if we do that, we will get the expression for GE, which comes out like this. Okay, the density of states is actually depending on the mass of electron as well as energy of the state, energy for which we are doing the calculation of density of states. What you can see from here is, I will come back to your question, Harsh. Just give me a second. I will just come back to your question. Let me just finish this thing. So density of states, it is proportional to e to the power half. From the bottom of the band, it is proportional to e to the power half, right? At the top of the band, GE should decrease because if you remember from here, up to a point from the bottom of the band, then density of states increases, then it reaches a maxima at the somewhere around n by 2, and then it starts decreasing. So from bottom, the density of states will be proportional to energy, sorry, e to the power half. It will basically increase with the under root of energy. From the top of the band, actually it should decrease as using this, like the dependence will remain the same, but it will decrease by by e top minus e to the power half. Here the electron, the mass of the electron which you are seeing, that should be effective mass of the electron. That we should remember, that it is the effective mass of the electron, and the equation is valid only for free electrons. Usually, actually, this equation is valid only for free electrons, but we use it, very freely for even for semiconductors and metals which may not have always free electrons. So that is an approximation which we make. All right. Okay, we will discuss this in the next class. But yeah, that's what I wanted to discuss about density of states. Now there are a couple of questions. If you have any other question, we can take them up also. How is it number of states? We have computed volume. What do you mean, Harsh? You can actually unmute yourself maybe. See this.
Sir, like
Huh, yes.
state should be proportional to the volume we computed and not equal to it. Like there should be some constant.
Can, can you just repeat what you said?
The number of states should be proportional to the volume we computed. So there should be some constant of proportionality.
No, no. See, actually, volume automatically came into the picture here. When we calculated the number of states, this is by simple, I mean, by this logic which we have used, right? When we replaced n prime using this equation, by by the energy of an electron in a potential well, there is a term L square here because there actually in that expression L is the dimension of the box, because actually the potential well is considered to be a cubical box, and there L is the dimension of each side. So that is why this L square is already appearing there. And when we calculated the number of states, it came out to be like this. This is the number of states because in the total volume L cube. If we, because in the definition of density of states, we need to have number of states per unit volume. So we need to divide it by the volume of the material, and that will be is equal to L cube. That's why this L cube this appears in the expression for SV. Is
Okay, sir.
right? All right. Yeah. Other questions? If you have any questions, we can start the next class. We can take up those questions. Are the number of integer points inside a sphere equal to its volume? It should be the case of a square or a rectangle. Yes, actually, that is an approximation which we are making. I understand your point that there will be some cubes or there will be some squares which will be only half cut. They will not be fully cut. So for that, I mean, we are not going into that much detail. This is an approximate way which we have used. All right. So we will, I think, when we do, like, if you want to write a program for it, what you will do is that you will take into account the boxes, which have more than half of the area in the circle. You will take those into account, and then neglect those neglect those squares which have less than half of the area within the circle. All right. So that's how you will make an approximation in that case. Okay. All right, I think we have already overshot our time by 10 minutes. So we can take up all the doubts which we have from this class in the beginning of next class, and then we'll start with the quantum theory of metals in the next class. All right. Thank you, everyone. Today there will be no tutorials.